guys, this is the first episode of Optimosophy, where I will finally present something a bit more interesting than the previous introduction, which was a primer mostly. So I'm going to present a trick that vastly improves performance, like 3 or 4 times the original speed, depending on the effect you want to optimize. I used to call this the 32-bit trick, and I don't know how it's called in reality in the programming world, and which demos ever used it. I'm pretty sure some demos have used it. I just haven't seen it mentioned in a certain way. And I remember it was the first time I started learning coding assembly, x86 assembly. I was using 386. Maybe I had a 486 or a Pentium 1 at the time, but I started using the 32-bit register. Previously I was using the 16-bit with segment offset, and that's where it hit me. Although the trick can be easily recreated in a C compiler, you don't need to do it in assembly, and I have written a lot of effects like that. And I was wondering then, as I was learning about the 32-bit registers of the 386, what else can I do with them besides bigger numbers? So it quickly hit me that in some effects with some hacks I could calculate and write 4 pixels at one in an 8-bit per pixel resolution, the typical VGA, 8-bit per pixel color depth, typical VGA color depth, where normally you would go byte by byte. Every byte is a pixel, so you would calculate your plasma algorithm or fire effect algorithm per pixel and write that byte and then go to the next one. But I found ways to do 4 pixels at one, and you will say, yeah, right, so you mean calculating 4 pixels and then meshing them together in a 32-bit register and write the register 1, or copying block of graphics 4 pixels at 1. Like, no shit, Sherlock. You think you thought something crazy? But no, it's not just that. I have gone a bit further than that most people do, and I have devised methods where certain effects, certain pixel manipulating effect, that where you think the pixels have to manipulate it individually, you cannot do it in groups, because they are based on different pre-calculator lookup table or mathematical data. Or nearby pixels, so you have to do it pixel by pixel. You can't do 4 pixels at one. That's what you would think. I would find ways in some of the effects, not all of them. There are some effects that this is not very possible, unless there is some more crazy idea. And you could do it. You could write the code in such a way, and maybe with some restriction on your data, so that you would do the whole work 4 pixels at one. Not just the writing, but calculating your effect with X and Y coordinate, but 4 pixels at one. But you would say, so is it some kind of blocky resolution trying to do this effect, but with 4 pixels, creating a big blocky pixel? No, it's still not that. You would see a pixel perfect 320 by 200 plasma fire effect and some other stuff I did. At least some of them that worked with this trick, because a lot of things don't work. You will see them pixel perfect, and I would do it in 32-bit register, 1 add, 1 shift, 1 read, write, and 4 pixels, the whole thing 4 pixels at once. So if an effect was running 20 frames per second, it would run suddenly 80 frames per second, or maybe 60, 70, because there would be some overhead with some corrections I would do to make this work. We will see that. And that's the trick I want to show you now. And I'm going to show you, I will continue with the plasma I did on the 386, because that's a nice base to show you some of the things that you have to take care. How you have to change your pre-calculation arrays for this to work in some cases. And I'll show you that and how it improves, and then I will briefly show you the other 2-3 effects. Maybe there are two more effects where I have used it, and the things I had to take care in those effects, and also the limitations. So you see some more effects where I had to use the similar idea, but how things were a bit different there. And there are effects that these things will not work for other reasons. We will see all that. And there is a phrase in Greek which is με ένα σπάρο δυο τριγώνια, which in English it would mean kill two birds with one stone. But I like to call it now με ένα σπάρο τέσσερα τριγώνια. Kill four birds with one stone. Because that's what it is. So I guess it's time to start, but I want to say, before starting with this the presentation of this new trick, I will briefly notice few points from my previous video. My friend Nuclear in the comments mentioned some things that I also noticed them. I just didn't go further why they happened. There were some weird stuff with the compilers not optimizing things well, and I was thinking then that maybe I can generate, present the generated assembly so that we investigate it a bit. But the thing is, yeah, my video was too big already, and I had to cut it. But maybe I will look briefly in few stuff, because I explore things a bit, and there are things I don't understand why the compiler is doing that. But there is some other things that I know the answer, and maybe I'll try to spend few minutes for that, so that it's not longer. And I guess when in the future there are some interesting comments that or things I have forgotten from my previous video, then I will have a brief section in the beginning where I will talk about the things from the previous video, or answer to some comments. We'll see about. It's time to start. Με ένα σπάρο 4 τριγώνια. So, to mention my previous video, before we start with the new trick, let's start with that. One thing that Nuclear mentioned, and I also noticed that when I was doing an end with a power of 2, here I'm doing the end, and this I already decompile it. Also, I move the frame counter lower left so that it doesn't flicker so much, so you can see it, and we will see the result also later. So that takes 7 frames per second, 7.26, whatever. When I notice when you use the modulo for the same thing, try to make this as short as possible. We are on the cycles for the same machine, 386 DX at 33 MHz, supposedly. I haven't tested this on the real machine. Anyway, the modulo thing, it has 4 frames. It suffers a lot, and my friend told me that, yeah, Wacom it doesn't optimize that. Normally it should optimize it. The GCC on the DJGP compiler optimizes, and it did. When I tried to build it with DJGPP, it didn't matter. So, but I think I know why Wacom does that. And this is, so there is a different, when you make an end with a power of 2 number, power of 2 minus 1, and it's a power of 2 modulo, and that the compiler will replace this with this normally, but Wacom doesn't do it. When you do it, then this side it has to be a positive integer, because the modulo on a negative integer works differently. It will regain the sign, and also it will flip, it will go 0, -1, -2, -3, going from the center to the left, while it goes 0, 1, 2, 3, going from the center to the right. So if you also do a rotozoomer using that and maybe put an ABS absolute on the result, you you will see your bitmap flipped in the 4-axis. But the end works better with that because it works differently. So the Whatcom couldn't predict that this is it always positive, so can it replace it with an end, or is it negative? It couldn't predict it unless I said, okay, unsigned int and starting unsigned int. You do it like that. And now it's 7 frames. Now it does replace the modulo with the end, because it knows that the thing it operates in is going to be a positive integer. And I'll say DJ GPP would predict that. And I guess it looked further. The optimizer is looking further. It says, okay, this is an integer. It's a signed integer, but it goes from 0 to positive. Okay. You see, it starts from 0. And this is an integer, but it starts from 0 and it only increases. So I guess DJGPP could predict stuff like that. It might be less safe, but looking at it, it's safe to replace it. That's the one thing. That's why Whatcom didn't dare to do it, and I guess DJGPP could still predict it from your code. And let's move to the other paradox. I have noticed that when I compile for DJGPP, if I enroll this loop 8 times, I get 12 frames per second. If I did that, which is the same thing in terms of pixels on the screen, but it's less unrolling, it suddenly does 20 frames per second. It's a bit better than Whatcom with 19 frames per second. So, and I still don't understand it. We are going to see the produced assembly in God Blood Compiler Explorer. I don't understand it exactly. So we have the Godbolt Compiler Explorer. I could also search for the make file flags to make it spit out the assembly, but I can see the issues here too. And DJ GPP 7.2, and that's the latest version. I don't even know the version I have, but the results are similar. So this one, you see it's repeated. Now this one, it reads move ECH from EBH plus EAX. They are set up somewhere. EBH is offset flat F sign 3. F sign 3 because it's this F3 pointer from F sign 3. And then the other one must be from F sign 1, this one. And the other one is a value I calculate outside. It's a console. It's stored on a register, on an ESI register. And and then it writes the byte because I write a byte at the end. So it writes the CL, which is the less significant byte from ECX. That's perfect. You see it here. You see it here. It's like I don't think I could write that faster. Okay. Although you never know. And with some other trick you can write it faster in other ways. But anyway, we will go that in the future. So this looks tight enough. And then you will just, it's the same. You go, I haven't figured, it's hard to read. You unroll and each line of this, you see, it's a big block, and now the code has changed. It it reads the BL from EAX. I'm not sure even those pointer above have changed. Something changed with it, isn't it? The pointer. It makes one read in BL. It adds in EBH and BL is the low byte. Another read, maybe another side. It moves the result to ESI. It reads again from BL, another read. Why? It adds that to ESI and moves ESI to EBH and then writes the byte. What the hell? Why the hell? I reduce one, it's still big. I reduce. When it's 5, it's okay. Is it about the sizes of the... So I'm not going to answer that because I want to move on the next video. I just want to show you some peculiarities. Is it something changed with the register higher so there aren't 3 registers to... Like, what the hell? And I'm wondering what Whatcom does it right, but I will need to find it. Whatcom. What is the compiler of Whatcom anyway? I don't know. Maybe Zig C++. What is that? Risk V, huh? Interesting stuff. What if we put that one? Same 03. See, it does it right here. There are some different. EDH plus 4 multiplied by EDI minus 28. There are some different stuff. Add ESI, add this. Right, it does it opposite. This one, C-Lang does it better. But it's not a GCC. x86 64 GCC. Where is it? Does the same big blocks again. You gotta see what these are normally. It's hard to follow which is which. Maybe it's missing some register the way it's done it. But why increasing that suddenly changes the whole thing? I don't get it. Is it a matter? I'll do one final experiment. Very fast. So what if I say, okay, what if it's a matter of this offset something? Maybe, no, it should have a very long offsets. Does that change anything? No, there are still bigger blocks doing more stuff. Well, that blows my mind. What if I don't have offsets? What if... Okay, I'm going to repeat this like 4 times. Okay. Small blocks doing what exactly? 5 times. 6 times. This is where it normally... Oh no, 6 times and it changes the whole thing. Oh 02. Same thing. I tried that actually. Oh 01. Same fucking thing. Oh 0 is the unoptimized. What is oh 0? It does maybe even more. Not sure. Oh no. Oh why? What? No, it's okay. I saw that red and I thought it didn't. Oh, here. My god, what the fuck? O2 is O2. I don't get it. I'm curious if it is. So, 486, because I had such problem. Cobile for 486. Same thing. Not this time. I don't know exactly, guys, but keep that one. Let's go to the original code. I talked about the weird stuff on the Cobile, but there is one little thing I noticed later, which is also a mystery. So I would, that's the old example. I use the end instead of the mod. It doesn't matter. I compile with, let's see, del sino. You need to do that for some reason. Okay, man, it could take time, so let's put it fast. I'm trying to do things as fast as possible. And put it back. So that's the original one. Okay, that does 10 frames per second. That's how much it did. And as I was exploring things, I decided to reduce the optimizer to O2. Even O1. Same thing. Okay. I'm deleting the object 5 because for some reason it doesn't delete it. And I was doing tests and I was getting the same results and I'm like, what the hell? It was rebuilding the exe. Normally the make file should. So I don't know. I don't remember this issue. Anyway, so with optimization 2, is it O2 here? Oh, why is it faster? 12. 12 frames per second. 11, 12. Maybe it's accidental? 11.78. And even when I put it in optimization, one lower level optimization, and I need to see one day a lot of this optimization flag, what they mean. It was still 12 frames, so it's better than all 3. You see, sometimes I know I have seen a lot of projects that they use O2, and I'm like, why don't you use O3? And usually it's supposed to be there are some more extreme and unsafe optimization, and people say, okay, O2 is enough, don't go to O3. It's like I have seen it. O3 is also fast, by the way, and there is another one for size, and there are more stuff. But I put it O3. There are few cases that I notice a slight improvement, but here, why do I get 12? Okay, I was going to put this in Godblood, but I would have to put the screen structs and a lot of other things. Not that it's so hard, but I found the answer. The previous code, if you have seen, it was getting screen height and screen width. Now, but the O2 optimization was a bit faster than the O3 because of that. It seems that's the case. When I do, I have talked a bit about, you know, you can put this in cons just to be sure outside, because now the compiler will generate a entirely different code. And now from this one, I build an optimization 3. You already see it. It's even better than the O2, 13, 14. 13 frames, 14 sometimes. About there. Conclusion, compiler is a bitch. And I wasted so much time for this. No, I will put it in the separate section and you can skip and go to the main one. But we have to see those things sometimes because they are so weird stuff that would steal your performance Also, the main goal of the channel is to show the big tricks, the ones that will not give you 10% performance, but much bigger. Sometimes. So it's time to start with this new 32-bit idea to write 4 pixels at once and do all the calculation four times at once. And to explain it, it might not be easy to explain. It was something that I had visually. And maybe that's not the best schematic to explain it, but initially you had a function that was the plasma function. Okay, it would get data related to the first pixel to at x0 and y whatever it is, make the calculation and write back at 0 comma white this pixel. Then you will do it separately for this pixel, and this pixel in an 8 bits per pixel color depth. So, and that's how you would normally do it, pixel by pixel, because every pixel might need different pre-calculated table related to its XY position. And the whole goal of this trick that it's easy in some effects, it's very hard in other effects, or it might end up being too complicated and losing more performance. The goal of the idea is, what if we had chunks of specific data, specific pre-calculation, specially tailored for the occasion and with some restrictions, and we could run some kind of function that takes the 32-bit integer value, does some kind of calculation, and it returns a 32-bit result, which is the 4 pixels packed together. And if you can easily use whatever the G function needs, sign lookup tables, neighbor pixels, other kind of lookup data, if it's easy to relate series of data, 4 bytes that is in a 32-bit array, to relate it with the algorithm so that you operate on these chunks of 4 bytes and somehow gives you back the packed result of 4 pixels at once, then we might speed up things 3 or 4 times faster, depending. It might be that doing this method you might find some issues and you have to do some extra correction on the bytes so that they don't overflow. And there are algorithms, I will show, there are algorithms that this is impossible without unpacking everything. There are algorithms where you have to unpack the 32-bit result in 4 bytes and do more stuff and then pack. So there are algorithms where you would end up, this would end up here, but then here you would unpack again the 32-bit result in 4 separate results and pass it through another function that maps its separate byte to its separate result value. So there are specific algorithms where to find this special G function is going to be slower. It's going to be more cumbersome, and you will end up writing more slow code than just doing it the way it was here. So in order to explain what I'm trying to do, we could go back to the example from the previous introduction, which is the plasma effect, and I remove the unroll code so that we work on a single line, and then I'll put the unroll back if we want. But now the thing is, maybe I'll explain something more simple. Forget about this equation. Say that you have, just go and write crude code. You have this one, maybe put this one just for, so it's going to be a bit of pseudocode. Say that you have this one, and you really do something more simple. You say that dst plus plus equals fsin1 with x value. And maybe this y is redundant, but okay, we'll see. It doesn't matter. So dst happens to be an unsigned int 8. It's a byte. But the sign happens to be, okay, I use ints to store them, 32-bit numbers. But the value is still, it's a small value that could fit in a byte. Now, here, when I calculate fsin1, it's a sign multiplied by 45, which means goes from minus 45 to 45. Yeah, so, and here's the thing. The first idea is that if I add 45, it's going to go from 0 to 90. So this is a number that fits in a byte. And I could make them into unsigned chars, uint 8. And I could do the same. Now, I'll show you some issues that we might have. We'll see. Now, let's see this simplified pseudo example. This is a byte. So, if you have 4 pixels, then, okay, maybe I'll do it with tabs. Then the result will be maybe more tabs. Okay, but you might notice already something. And what if I create a new fsin array, fsin32, where at 0 it is going to be fsin1 0, and I'm going to use some shift to make you understand. I'm shifting the byte on the left side, or fsin1 1. Okay, so you could construct lookup tables with 32-bit values that have the 4 signs. The lookup table, the pre-calculated signs, they are in a row, 0, 1, 2, 3. And that loop could be uint unsigned in 32 ds 32 is uint 32 pointer. I'm going to cast dst, and I could do that, and I could call it fsin32. And here it loops from 0 to width, and I could do that, but no, since this is for 4 pixel and the next one will be fsin1, that will have fsin4, 5, 6 and 7. This should rather be plus plus, and this width should be divided by 4. Because it's going to be operate in 1/4 of the values on the width. If the resolution was 320, this would be 320 by 480. Of course, we can normally do constant width 32 equals width for. And this is for the very simple. This is a very. It's not even a plasma. It might be a horizontal wavy thing. Okay, this is the concept, man. This is what we will try to do, and we'll see on some issues that would arise. So let's try to do that. I should make it for the three signs. I'm going to show you the issues. So I guess in 32. I have this special types. This is unsigned in 32. And I will keep the same names, but I'll know that they will be of 32 size. I paused a bit because I thought, oh, how could I do it? Should I do it like that? Should I make yet another array, fill the memory, and copy those to that, and then delete those arrays? Or so. But you know that you don't need it, because you can simply say, for example, uint32 pointer fsyn ena 32 equals uint32. You can point a 32 pointer on the original. So if this one starts at 0, which it does, this one now points on the bytes 0, 1, 2, and 3. So you might not even need to create it. You might need to create some other arrays later. We will see it. We will see it because there is a catch. So maybe we can start even if those ones. Oh yeah, okay. This used to be in integer. Because I was working with integer, I didn't care. So we make it a uint8 so that if we cast it as uint32 now, every int would be a byte. Previously, every int would be a 32-bit. But we made the signs in such ways that they fit in a byte from 0 to 256 maximum. So we might need to create an array later. There is a special case. We will see. You know something? Because I also have trouble thinking about it. I decided to simplify it, and I have trouble to teach that. So I commented everything out, and I say let's say that this is the simple equation we have for start. DST is still on uint8. We are going to see the byte version. Okay. Let's see what it displays, because I don't even know. We don't need now. We are going to be in very high cycles just to compile. If I make it work, then I will switch to the 386DX for comparison. Let's see now. Okay, see it display. It's the sign value relative to x. So you have vertical bars that, if you could see that from above, it would be like waves. Okay. So now let's see if we can display the same without breaking things up. We will want to work 4 pixels at once, so that we will make uint8 32. I'll call it DST32 so that we know what. I will cast the start of the video RAM address as DST32. I will have to. Now technically, if you do that, it's very possible that the compiler will, since this is a constant, it will divide by 4 and it will be like a shift by 2. But you know what? Just to be sure, I'm going to do this here. So I divide by 4 because now I'm going to loop 80 times instead of 320 to jump over 4 pixels at once. That's the trick. So this one is still a byte. So I will have outside here, and let's make it clear, u in 32 f in 1 32 equals u in 32. I'm going to cast this as a u in 32, and let's see if it displays correctly. So this one is doing the same, but doing 4 pixels at once. It reads a 32-bit integer from a unsigned car sign table, so it reads 4 sign values in succession, and it writes it back in succession on the Vidor. I mean, that's like copying a sprite 4 pixels at once, really. Okay, so that's the easy part. So now, the good thing with the vertical one, and that also has the scrolling thing. It adds the frame now, we will see. The good thing is that it's... Let's do it one by one. It's happening in the outside loop, so we don't care much. But here is the thing. I will show you what I will do here. It's in the outside loop, so we can be more free. This is not going to work if I goes to do that fsyn 2, and I will show you why. If I goes to do that, so let's do sign y to read 4 pixels at once, 4 sign values at once. It might work in a way. Maybe I'll do it unsigned in this one, although it might not matter. But it's not correct, I will tell you why. Oh, it does something, but it's weird. Yeah, now you are making me to put this. You might say it's correct, but we would have to compare it with the original, normally. Actually, why is this not correct? Because this transformation is working on 4 successive pixels residing on the horizontal axis, on X, and not on Y. Do you get it? So it is for pixel 0, y, 1, y, 2, y, and 3, y. But wait a minute. The original code, let's see if we can go back. The original code was operating on the y coordinate. So, wait, what? So I have to bring this again to explain. What's really going? You have fsyn 1 x, now it's a 32 value, so all those 4 pixels at once in one bunch, 132-bit array, and you add the fsyn 2 based on y, but it's always fsyn 2, it's fsyn 2, not fsyn 3. Is it fsyn 2? Yeah. Okay, sorry, fsyn 2. So it's based on the same y coordinate. So if y was 0, it would all be 0. Because it's not relevant to the x coordinate, and the signs are linear, the successive on the x coordinate from 0 to 320 or whatever. So you're like, okay, what do I do then? What you have to do for this case is, okay, you have this psi2. You create here. Now you can do it. This is a bit of extra code, but it's happening on the outside loop. So there is not much performance loss. We have to construct a 32-bit value that has the same psi2 copied 4 times. And I assume most that watch this one and they are programmers, they know about the shifts. So I packed the same C2 value in the 4 bytes. So now I can copy this one and produce this here. This is to show that when you do this whole 32-bit thing, the G function transformation, you have to do a lot of tricks depending on the total function that we have. And we will see the F3X later. That is, even this one might not be perfect because there is an offset on the timer. We will see that. Oh, what happened here? So maybe that looks better. It kinda worked before, but it wasn't correct. And you could see some artifacts. Now it's smoother cycles. Okay, it was. You would see broken cycles. But there is not much animation because we have to put the final one. The final one might be easy, but we have to take care of something. Even for this one we have to... this is on the outside loop, so it might not affect performance much. And also this is a performance that I don't know if DOSBox 6 emulates. We will run it later. We will run the resulting one on the 386, but I'm going to have to speak about some things. But I think this will work. But there are better ways to write it. Now, this was a bit tricky because we used to have... This was the final one. And why is it getting the address of fsyn3 on the y coordinate and then is using it on the x coordinate? Because the original function was fsyn3 x plus y. I put x plus y, you can put anything, x plus 2y, 3y. Okay, I put x plus y to create a bit more interesting plasma, to give a diagonal view. So, technically it should be possible to go here and do the transformation here. Let's see. Now, I used to cast it into int because this used to be integer, not uint8, but integer, even if they had byte values. So, I prefer to call them, it's the same, uint32. No, but now this one is an 8-bit. But we are going to cast at its base address plus y. The y offsets it. But then it's offset again by the x here. This pointer. So now maybe this will work. I will call it f332. But now it's f332x, I think. Let me think about it. Since this is a 32 pointer, it points at the byte address, but then it moves 32 bits by 32 bits. So it's going to grab 4 blocks. Like here, it's going to grab 4 blocks at once, but they would be offsetted. And maybe that works. Maybe it hasn't destroyed my plasma. So to do these tricks in various effects, you have to take a lot of consideration, and there are more. We will see. Oh, it works. See, the frame rate is 36 frames. Previously, okay, it's not 4 times faster, as you see. What was the... Previously we achieved... okay. We achieved 19 frames per second. But we achieved... see, it runs 30... But we achieved 36. Actually, let me see something. Okay, previously... 36, we achieved 20 frames per second. But that's because we unrolled it. Now we remove the unrolling so that we can work on the effect. And we will unroll it at the end. Actually, we can try to unroll it now. See, this is the 32-bit. So previously with the unroll, we got 20 frames per second. Without the unroll, I think I got 10 frames per second or 12 frames per second. 12 on DJGBP. And now, without the roll from 12, the same plasma, it goes 36. It's 3 times faster. Maybe because there are some reasons. First, there's a bit of extra work. You have to create the Y2 to make this the same value 4 times so that you can add it. Because it's not based on the X coordinate, we have to do it like this. It's the same value 4 times. But this one, the address is not initially not based on X coordinate, but then we do X plus Y, so it has to be based here. But the initial offset can be taken with a Y. And there are some things I want to see. I might not unroll it yet. We get 36 frames per. Let's see if DOSBox emulates an issue. I'm going to. Yeah, okay, I'm going to do some kind of hack. Let me think. We are going to have a stable, a plasma that doesn't move. It's going to be a hack. And I will tell you why. Let's do that. I'm going to explain that. We don't care much about this because it's in the outside loop for now. I want to see something if the performance is affected, if DOSBox emulates this issue with the performance. This one. I can simply put it to 0. We might see a different pattern. And it might be obvious for some people. What? Will we get 36 or will we get a bit better? Let's see. If DOSBox is not accurate one enough. Okay, we still get 36. And this is a more static pattern. It's just scrolling. So I'll try to explain what we have seen on the real machine. Although I was expecting that one of the two cases would be much slower. One was 42 frames per second, the other 39 frames per second. I was expecting to see more penalty. And the thing is, these are the signed tables we read, and these are 4 bytes in a 32-bit block. And I have put the red lines to show that the arrays are usually aligned in 32-bit aligned well. So the beginning of the put another color. The beginning of this address, the first byte here could be 0C. I'll just put that. Then this one here is 4 bytes later. This one here is, and so on. Okay. So if this initial pointer, if it goes at 0, because it happens on the compiler will this original arrays, it will align it well. If it goes on 0, or if it goes on 4, or if it goes on 8, or if it goes on 12, it would fall in the beginning of the red lines. So you would grab those 4 sign table values and do what you do and write it in the pixel. The pixel destination are aligned well. But if you move it in an offset, if instead of 1 put it from 0, you put it to 1, 2 or 3. If you put it to 1, we might try to grab the 32-bit block here. But this is between the aligned lines. lines, and x86, there will be a penalty on x86 because it will have to read both this one and this one, get those 3 bytes and that byte, scrap the rest, and create the final 32-bit value with the 4 bytes. So it has to read twice the stuff from memory, because your read is offsetted in a way that is not aligned. And in fact, if you do this in some old ARMs, if you do it on the 3DO ARM, it's going to even crash. The emulator will work, the real machine will freeze. That's how bad it is. So when you do these 32-bit tricks to read four stuff at once, you have to be careful of your alignment. Now on the 386 it works, but there are penalties and you might not see them. And that's why it goes a bit slower, I think. Because initially we wanted to do the x plus y, that's why we do the y. We get the address with a y offset, and the y goes from 0 to height, it goes 0, 1, 2, 3, 4, 5, it goes 1 by 1. So 3 out of 4 lines in your plasma, 3 out of 4 scan lines will have an offsetted read for this one, and that could give you a small penalty on the x86. So that's a little detail with those tricks. It wasn't as significant, but I will show you how to fix it. So it's time to do our memory wasting trick, so that we always have aligned reads, and the only culprit is the FSIN3 in this plasma equation. If you were designing another plasma equation, then you would have to handle things differently. It depends. This whole trick you have to manually handle it depending on your effect, depending on what you do. So this one, we want to avoid the unaligned memory reads. So we are going, here is the fun, we are going to define 4 of them. It's going to be fun. Maybe a waste, because I see there was an overhead, but it was small in our case. There was an overhead on the real machine, but it was so minimal that you could. But I want to show you that. I want to show you that there are these issues with this trick. So, and now FSIN30. So we created 4 tables with offsetted sign value. Offset 0, offset 1, offset 2, offset 3. So instead of offsetting it by y, you will see. It's a waste though, but so this will be that copy. Oh, hold on a minute. Ooh. Ah, yeah, I think you gotta do that. You gotta offset. So it's like you create 4 versions of the lookup table. Each of them offset the y, the x, or the I. It doesn't matter. Offset the index by 1, by 2, by 3. Okay. Yeah, I'm wondering if there is a better way. I know some better ways, but I want to do it in a lame way so that I finish with this video. I end, or it's like a modulo, but okay. Doesn't matter. So I want to see if I'm in the scan line 0, scan line 1, 2, 3, 4, 5, 6, 7. I want to see in which offset I am. And I could say if then this one. This is very lame. I think I have done it better. But let's do it like this. Okay, let's trust me. This is very lame. I just want to show something. There are many better ways to do it, but now I don't have the... So depending of the offset of the y coordinate, if it falls at 0, 1, 2, 3, so that we know we avoid the unaligned, and we assign a different array, which is the same array. This is the same calculate array with an offset. So we waste 4 times the memory. And you might not need to do it. We just want to see. And that's okay, it's on the outside loop, so it is a bit of wasting. Let's see if it works first. We will see if it did matter on the real thing. Oh, we even did something wrong here, man. Something is wrong. It's very squarey. Yeah, look at this. Equals equals equals. Yeah. Yeah, that was dumb. See, a little thing. I think now I'm just going to show you, you learned the main optimization trick, but there are more from the previous bit. But I want to show you the madness. I guess I'll keep those clips. It's still squarey. What the fuck? See, it's hard to make it work, but why? Yes. So there are these little details. This is an offset of the values by +1. So I think you have to do that to go around. So we want to get the first value for psi equals psi being offsetted, psi equals 1. So, but because these values are moved to account for the offset, we have to do -1. So if psi is 1 or if psi is 5, we get the value at fsin 3_1 at 0, but the value of fsin 3_1 at 0 is I plus 1. It's 0 plus 1, it's the sign for 1. So if psi equals 1, we have to get the value at 0. That's why we have to subtract in the opposite. This is turning, I think this is a waste, but I have done it much better. You could stop, you could have a fast plasma without this. This is to avoid the misalignments, and I see now that they weren't very serious. Hope it works now. Now it works. Now it doesn't seem cropped. And let's see if it matters for anything, because even if this is in the outside loop, we're doing a lot for the outside loop, and maybe we won't see the gain. I was thinking, okay, there's a better way to do it. Maybe let's do it. Maybe let's capture it and do it. Okay, I'm going to create and that would be dump. Yes, I had to try. I was doing something for this video and scrap the whole of it, but I have to try again. And I'm not showing you the process, I'm showing you that because I tried it on the 386 and it increases 1 frame. But the previous version, where this was 0 and nothing was happening, it did 43 frames, I think. Now from 39 it's 40, 41. So it was losing a lot from this kind of if-else statement. So I wasn't sure about it. I did an array of 4 pointers. I put those 4 in with the 4 offsets, and on the y coordinates and 3 it goes 0, 1, 2, 3, 0, 1, 2, 3. So we are selecting each of these pointers, not the if else statement, but with a mapping, and we have to subtract itself. This is the weird thing, because if y is 0 and you happen to select, if y is 0 you will select, if y is 1 you select that, 1 plus 1 is 2, you have to subtract it, so it's 0 plus 1. It's so weird, man. And initially I was like, wouldn't that crash? If y is 0, wouldn't that crash? Yeah, but if y is 0, y is 0. If y is 1, y is 1. Now, if y is 4, y is 0. If y is 5, y is 1. 5 minus 1, 4. See, so it brings it at the position you want. And so I did that one. Let's see if it crashes, because I don't know. And then we will see if we, with the previous hack, we lost some speed. We gain some speed with the aligned reads. Let's see if it works first. Okay, it works. It's weird, man.
So, let's see it from the beginning. Now let's put the last version. Let's not drag it further. (4041). Huh. It's a more stable 41. Okay, I guess from 39 to 41. So I don't know. The first version was... No, this is the one without the animation. That gets 41 now and not 43. No, wrong. No, it was that. This was the unaligned. Now it gets worse. There's a reason, man. There's a reason. 38. Okay, here is the comparison. It's in the same setup. For some reason, when I reboot this machine, the video output, sometimes it's 76 frames per second, sometimes it's 81 frames per second. I'm running some benchmark, and every time is random. Now, to make this video, I had to power off the machine and power on many times. Okay, so now this is our comparison. This is the unaligned. In this one, one of the signs are doing unaligned reads. Okay, maybe the unaligned writes are worse, I don't know. And it gets 38. And the final best fix, but with four times the memory waste, it is this one. From 38, okay, that's a good difference for 41. It's more stable on the 41. And maybe, okay, maybe this is insignificant in this case, but if you have some other effect with more reads, it matters.
Is this one? Actually there is one more thing. Yeah, I need to talk about you, but we're gonna see it later too. If you do this thing, if some of the operation of the function on the 32-bit blocks, if it's multiplying the whole thing, adding, and there is overflow from byte to byte, you might see artifacts. Let's see if this happened, because I'm not sure. It should have happened. If I wanted to make bigger signs, okay, maybe to see what I mean, maybe make it slightly bigger. This is from 0 to 190. 226. Maybe make this one. Sorry about that. That's another thing I wanted to talk. That's another pitfall you can fall in these effects. Because, okay, if you have, okay, I have those numbers. Let's see that you have some sign values. And my gx whatever here is sin x plus sin x. Now that's a stupid example. So you add those values to themselves. this is 400 now, this is 402, and so on. So the result of those 8-bit values, but that they are packed on a 32-bit value, will overflow. The result of this addition here, it will overflow a bit here. The result of this one, it will overflow a bit here. It's hard to show, and I'm just doing scribblings. So that's another thing you have to be careful. So if you are about to use big number, I was expecting things to already break with those values, the previous values. Now this is bigger. Now this one alone is from 0 to 240. This is fitting in 1 byte, so it should be fine, shouldn't be? But it might not be fine because we are adding all these things together. It's like we take yeah, 4 things and adding them to 4 things together, but they will overflow in the next bytes. Since we do it in a packed format, not separately. If it was a separate byte, it will overflow on the processor and it would give a looped value. Maybe it works, I don't know. Maybe that's okay. But there are other cases that you have to take care of this, and we will see that. And I'm sorry for dragging this video so much. Again, it takes me more, but you know, I'm going to accept it. It's going to be Optimosophy crazy. Okay. You know, the overflow is not visible because, yeah, interesting. Also, I have arranged the palette. Maybe that's why. I have arranged the palette that the palette loops, and maybe there is an overflow on the lower values, but this loops well. Interesting. I thought that would be a problem. Let's try some crazy stuff. And here, if it, I thought for this trick you have to reduce your the amplitude of the signs. We haven't seen one thing though, but it kinda works because there is overflow from the high bits to the low bits of the next byte, and it's because the color is smooth you can do it. But I want to see. Take it back. What is this? Scribblings. When I started, I offsetted the signs so that I don't have the negative sign. Maybe the negative sign is a bad idea. So what if I don't do this offset, and let's see if now it's broken. Let's see this. I'm doing this extra stuff. One would say you should stop now, but I'm doing this because we have to see those special cases sometimes. We have to see that when you do tricks like that, and even in other algorithms, then bad things can happen and you may have to. So initially you will think, oh, this doesn't work. It was a bad idea to even try. But no, because you might fix it. It's okay, but do you see some vertical scan lines? It's the negative numbers. There are some tiny vertical scanline artifacts. It's some overflow bit from the negative. A negative number, a -1, if you convert it to its FF, it's 255 really. So, but I'm surprised that this works. It works. So there are tiny artifacts, but it still looks like a plasma. It's passable. Okay. But even that works. Interesting. But can I have the original values? Just because? Because I was okay with them. So, and now we have to move to the final part. We have seen the cases with the big numbers and the negative numbers. For a plasma, this whole trick will not create problems. Yeah, you could have scrapped a lot of the crazy optimization, those 4 times to avoid this alignment. Okay, from 38 frames, 41. I just want to show you that when you do these tricks, you have to be careful of the alignment. And if you want, you have to do hacks. And this, without this alignment, if I port this on a 3DO with an ARM processor, there will be a freeze. The misalignments are not allowed on the ARM. It's going to freeze the whole system. So this is necessary if you do this kind of optimization there. But on an x86, okay, there might be a penalty. It's up to you if you want to go the hassle. But to finish with this one, and also I will show one or two effects. We'll see. Maybe I will talk briefly that there are few more effects where I use the same trick. We have to see more effects and the culprit's there. But to finish here, I'm going to unroll it. And I like to unroll it 8 times, and I'm not gonna use DJ GPP. I don't care. Maybe it's okay. And we are going to try it on the real 386 just for comparison. I think it's alright. This one is not based on X. And also, what are we unrolling? You see an X, but that's not an X for pixel cord. This is on the 32-bit. So when X is 1, it's 4 pixels to the right. It's really like 4 pixels. These values, because the width is divided by 4, so it's from 0 to 80. And now we have unrolled it 8 times. So if you divide it 8, it's from 0 to 10. So that would be fine. It's divided exactly. If we unrolled 16 times, maybe we would have problems. Actually not, because 80 by 16 is 5. But 8 is enough. 8 is my limit for this now. Also in the next chapter, in the next video, I'm going to show you a magical unrolling, where you unroll everything. And how it relates to retro 8, because here we do small unroll, either 4 or 8. I think 8 is the one is the sweet spot. If you go 16 and later, you don't see much difference. But from 4 to 8, there is difference. Screw DJ GPP that with over 4, it does weird stuff. I don't care. I think it's okay. This one is the same. The same for the same scan line. Okay, and maybe I should shut up and try it. We are still in 386DX33. It's interesting. In the 386DX40, okay, it's 40. I thought because it's a real PC it would be much slower, but it does a bit more than this one. So it's, if I test here, I might be okay. Yeah. Look, huh? 68 from 30 with the unrolling. Do you remember the first episode with all the unrolling and it was byte by byte, and we did 20 frames per second. Okay, now we did 68, 70. No, it's not 80. It's not 4 times. It's 3.5 times. So when you do this trick, you might get the speed up close to 4 because there is some overhead. There is an overhead here with the stuff we do outside, and maybe the generated code has an overhead. And maybe there is an overhead we will see on the real thing. Also now that's much better, because you write 4 bytes at one in the video RAM, that writes directly to the video RAM. There is no back buffer. So that might be, I never tested the byte version on the real hardware. It could be much slower. So, see that, 69, man. 69, wow.
So we could try the final result, but I also want to show you something about my 386DX. 386DX at 40 MHz with the fast, they have the eyes slots. They don't have any local bus or PCI, and this is a slower slot. And the fastest cards you can find is the Cheng Labs ET4000, I think. And every time I boot my 386, I have to tweak some things in BIOS. And I have to make sure that I get the good numbers on SI, just to be sure it doesn't underperform compared to the 38633. Because sometimes, and then I run DX project. Also, I have my own benchmarks too sometimes. And this one has a check where it tries to run to the 320 by 200. And it gives, that's one of the best numbers I get, 82 frames per second. I get between 76 and 82, and that's a good number for a Cheng Labs. And if I reboot the machine, I might get 76, for example. It's a bit random. But I know that these are good numbers. If you have a Cheng Labs and it does 40 frames or 20, something is wrong, or maybe a jumper from the card is out. Or I have one that seemed to be faulty with some. It was creating some issues on the display sometimes, on certain resolution. Maybe a memory was bent, I don't know. And that one was doing 20 for a Cheng Labs. But this is always to ensure that I have the maxed out 386 for my test, and it's the same. Now, sometimes I reboot and I get 76 frames instead of 82, so the frame rate is variable. Unless your effect is very heavy on the CPU, of course. So it's a matter of your CPU rather than. Now I'm going to copy the final versions, and I guess, you know what, I will also try the DJGPP version. Dior. Let's try the welcome. That's the unrolled one. The final unrolled. Takes. See, it's a bit slower because of the video RAM. Even if it's 8, there is some overhead with the effect and some overhead. But okay, 57. That one was a bit faster on the beginning. Still okay. We managed to do a full screen 320 by 200 per pixel precision, no blocky pixels, at 57. And I'm sure if I write it in assembly, I can get a bit more. Okay, let's see I'm curious about the DJGPP here. Does it give some extra edge? Did it crash? It takes some times. Oh, could have crashed. Hope not. Maybe the sign take more time. What the fuck? Shit.
So, before I finish with this Optimosophy episode, I would have liked to show you the same 32-bit trick, how it applies in various different effects that I have done. And every effect you have to think a bit differently, because there are other issues that arise, different compromises, and you might be compromised in various things. You might have to use simple textures and fewer colors. And I'm going to have to be fast with this because the main video took more time than I thought. So in my demo Goldilocks, there are two effects that I use this extensively. It boosts up the speed. It boosts up the speed that those two effects run well even on a 386, while the other effects run a bit slower on 386. And that's my Goldilocks demo. Now, okay, the first one is the blur. Not the galaxy. The galaxies are dots that are drawn. Okay, it's drawn. But the final blur effect. This runs pretty well even on the 386. Especially here, let's see. When it explains, it's full blur, full screen blur. But do you see also? You see there are some vertical patterns. I mean, even here. This is has to do with the compromise of the trick. You see, it's every 4 pixels, but still does it works with the effect. And the other thing, this is very slow. No, it's not this one. And I could have optimized this maybe. And this, ironically, those plasmas, they don't use the trick. These were slower versions. Because they are in a window, they are still fast enough. And the polar plasmas are harder to make it work with the trick. Now, this is the... Okay, is it here? This one, believe it or not, it's using the 32-bit trick to do mapping of 4 pixels at once. And before the logo appears, it runs fast on 386. When the logo appears, because the logo is an optimized render every pixel, and if the pixel is black in front, it's a second layer where I do it byte by byte. And I could have written some speed code for the forward logo to write 4 pixels at one in some cases. Although it does this dissolving. But before the logo appears, this runs pretty smoothly on a 386. There is a restriction. I use the XOR texture, and someone told me, "Oh, XOR texture again. Why not use a more better looking texture?" And the reason is because of the compromise. And maybe I will try to show you some things in the Goldilocks source code, but I will try to be very superficial because the time is over, and maybe I'll show some schematic because it's a mess here. The way I did it is a mess. There is an unroll macro. I'm doing things outside and inside, but generally speaking, I have a loop for every pixel on the screen, but I'm see RAM32. I end up writing for an unsigned int, so it's 4 bytes at one, 4 pixels at one, and somewhere here the color, which is also an unsigned int. I'm adding the color that from the previous loop. That's another trick. It's hard to explain. I'm adding values from the fire buffer, but it's buffer 32 plus 1, buffer 32 plus VGA M13 width. This is the 320 bytes in VGA divided by 4 because we are moving on an unsigned int pointer and not a char pointer. Minus and plus above and below. I'm doing the shift right by 2 to divide the 4 pixels added by 4 to take the average of the pixels, but it's not pixel, it's blocks of 4 pixels. I need to show a schematic. And also this one is a C, it's not another int. It uses the previous value. I need to see it because it's pretty complicated. That's a trick. The C one I used it on the Amstrad CPC. The Amstrad CPC doesn't have a 32-bit mode. It was byte by byte, but it was a way to have to read 3 pixels, since the previous pixel was calculated before. But the thing of the story is I'm adding 32-bit blocks of pixels from the buffer, dividing by 2, and this is also important. I'm doing an end. This is a correction for an overflow, an underflow of bits. And I think I'm shifting left by 1 because the result of this would be 0 to 63, but I have 128 colors in the palette gradient, so I shift them back for some reason. It depends on how you set palette. And here in the tunnel effect, I'm doing a lot of I'm not going to explain exactly. I might show you some schematics later. And I'm precalculating as the static, I call it tunnel, but it's the sphere mapping effect I showed you previously. It's not a tunnel. I'm saving this, maybe it's this pixel and this, why? Every pixel in the screen, I'm saving the U and V coordinates of the texture. So that I take a specific pixel on the screen and says this will map to that U and V from the texture. But that's an unsigned chart, it's byte per byte. Okay, and the texture byte from 0 to 127 or 0, I see I end with 63, it's from 0 to 63 for some reason. And I add a 32, so. No, it doesn't matter. At the end, it's ended with 0 to 0. I have a smaller texture for some reason. But this maps every pixel to... but then I also have... And this is the... I have unsigned tables. This one is tunnel size, the size of unsigned chart. If it's 320 by 200, it's 64,000. This one is tunnel size fourth, divided by 4, so it's 1/4 of this. Yeah, because every element of the array is 4 bytes, so it has 4 pixels. So I will pack this UV information in 4 pixels. And so then after I calculated this, which I allocate and I free later because I don't need anymore. After I copy the bytes for the dspics to the 32 bytes. And you know something, man. You know something. I didn't need to do that. As you have seen previously, I could have say dspics equals. I could have the 32-bit pointer point to the, and this wouldn't be arrays. I didn't need to do this extra copy work, and then work with those, and no need to free those. Okay, I could have done it better, but it doesn't matter. Now I do this packed format so I can do my 4 pixels at one trick, and I think this is what I aim to do. This px32 and py32, they are outside of the main loop, and they are, I even do some, okay, I think they are based on a sine and cosine. This is for the movement, sine and cosine movement, so that the texture scrolls around. For some reason I make packed, yeah, these are packed offsets that are added in the original U and V coordinates. So the U coordinate and the V coordinate, but these are 4 pixels, this is a 32 pointer pointing to a pack of 4 pixels. I don't have to do it pixel by pixel now. I take the U coordinate, I offset, the same offset is copied 4 times, so that I will show you in the schematic. The U coordinates are offset by the animation plus minus sign. Actually, I do 32 plus 31, so it is from 0 to 63. And previously it was 0 to 63 the texture. And I do the same for this coordinate, and I XOR them. So I get the XOR texture, and I XOR the 4 pixel values with the other 4 pixel values, but I XOR the UV coordinates, and I write them. So I'm basically mapping XOR texture 4 pixels in once, and this is the loop over the whole frame buffer, tunnel size. This is 320 by 200 divided by 4. So with the 16,000 loops and direct 32-bit writes, I can make this almost 4 times faster. I made the same effect in some 3DO code. Also the fire effect, I tried it on 3DO. I just haven't... I think I had the video preview. So this is easier to explain. I'm going to talk about the fire effect too. And I wanted to say why... Okay. So what happens with the tunnel? I have an array for every pixel on the mapping sphere that maps the u coordinate at the xy pixel. So u at 0, y, u at 1, y, 2, y, 3, y. These are 4 pixels in succession that I grab from a 32-bit block. And then I have the other array pre-calculated that has the v coordinate in the same arrangement, and I just grab 4 bytes and 4 bytes in one 32-bit read each, XOR the values together, because the exclusive OR is not going to overflow any bits. It's going to take the bits above with the bits below and do the XOR calculation. And so I have the combination U XOR V for every 4 pixels at once. And that's how you, with XOR texture technique, you achieve this effect. But here is the thing. If we wanted to use any texture with this trick, not just this XOR of 4x4 U and V from our pre-calculated tables, you would have to take the, you would have to take this pixel with that pixel, for example. This is for one pixel. Multiply V by the texture width plus U and read it from the texture bitmap. And then you have to do it separately for that. And I haven't found a way to do it for the whole block of pixels, because the textures mapped on the UV coordinate, they are going to be scattered. They are not in a linear form. Now, if you take 4U and 4V, they are linear, and you XOR them, it's a linear result, and you write back. But this one, no. It's hard to explain why, but this is one compromise. You had to do just, your texture could be U XOR V, or could be U something, U plus V, or U and or V. So you could maybe do some more noisy textures. But you cannot map with the 32-bit trick, if you think about it, because there is no direct... You have to break the UV separately and get them byte by byte, the way you would do it initially anyway, without this trick. So this trick is unusable with any arbitrary, nicely designed texture. That's why the XOR was essential there. So to explain the fire trick, 32-bit trick on the fire effect, I need to show that initially the algorithm was like that. This is operating on pixel by pixel basis. Okay, so this central pixel, you would blur it, and the way you would blur it is you would take x minus 1, so you would take this one, x plus 1, this one, you will add the nearby pixels together, x minus screen width to go above this one, and x plus screen width to go below this one. You will add the 4 nearby pixel values. They are all 8 bits per pixel, again, 1 byte each, and the result is 1 byte. You shift right by 2 to divide by 4. This is how you make a fire effect or blur effect. You need also a random base for the fire effect, but okay. And you write back the result. This is the result. And so now to explain the fire effect with 32 bits, maybe very briefly, because it's hard to explain. And I guess you get the main idea from the plasma, but to see the differences. And this would be the 32-bit version. I call it C32 because this is supposed to be just to denote that this is a 32-bit value and 32-bit pointers, 4 pixels at one. I say set the color, this big block, this red block, which is 4 pixels, is x minus 1. I say it's minus 4 if we talk about pixels, but if it's a 32-bit pointer, minus 1 will take you here. Okay. X plus 1 will take you here. And maybe I could render. X minus 1 will take you here. Come on. Wow, what? I don't know why. X plus 1 will take you here, and X minus screen width divided by 4, because it's a 32-bit, will take you here and here. And you add all these 4 blocks together. So you add like you are adding 4 pixels at one. And you divide it by 2. And I'm going to explain this one too. Also, let's say something else. Someone will say, let's remove that. But that's not correct. Because if you were to render 1 pixel, this pixel would be this one plus this one plus this one plus this one. But here you are adding this pixel and maybe that pixel, a very far away pixel for this one. And you are right, it's not accurate. You would have to somehow place this pointer here and this pointer here and do the thing. But this, as I said previously, this would give misalignment, misaligned reads, because the video RAM address, here it's at 0, here it's at 4, and so on. So this will be reads that will hamper the performance. And I think I tried that one too. I think it worked. But this one is a bit better for the performance, and it gives you that fire effect with those little grid lines, which are not very visible. Maybe I could have tried the other one, I don't remember. And also, if you did it like this, you would crash on an ARM machine, you would crash. If you do it not like I do it now. So this is, it's like a cheat. It's not precisely the original effect, but it works. It creates this blur effect with 4 pixels at one, so it's almost four times faster. I really need to explain why, as a self-correction, after I add the 4 pixels, but the big 32 blocks, and shift right by 4 to do the... I'm doing the divide by 4 by shift right by 2 in the 32-bit block of 4 pixels, but it's really like I am dividing, separating the 4 bytes. So I blur 4 pixels at one, but I have to do this correction. Why? First of all, I forgot to say that when you blur, you have to write something on screen, okay? You have to write points, you have to write stuff. I restricted myself another time. What I'm writing before I blur is the maximum value is 63, from 0 to 63, and there is a reason. Okay, so every byte I write is from 0 to 63. I don't go to the full 255. And the reason is, if I add here the 4 values, 4 nearby pixels, actually blocks of pixels, if everything is maxed at 63 and you add it 4 times, you will go to 255 at most. 252 really, 250. If it's 63 plus 63 plus 63. So you will never overflow. But now if you were to overflow in this byte, the bits would overflow in the next byte. So there will be bleeds from the previous pixel to the next. That's why this is 0 to 63, or it's those bits. But here is the thing. I have to explain it step by step. If you do this whole thing with adding around the blocks, and say your results before the shift, we haven't made the shift right. Result after add only, no shift. It's going to be those bits. It's going to be from 0 to 55 or a bit less. If you shift this, because you shift the 32-bit block of 4 pixels, you don't shift separately every byte, there will be some bleeds, not overflows, but bleeds. Those ones will be shifted, everything will be shifted here. Everything is shifted. This one comes here. But those bits will be shifted here. This one, of course, will be shifted here, but it will receive the bits from the previous pixel, which is wrong. And it will do some bleed artifacts. The same here, these are bleed artifacts. Also, since we are working from 0 to 63, these are the maximum pixels anyway for every byte. So we can freely remove those extra bits that might be bleeds. And this is really what this and the final result with 3F, 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 3F is. Because really 3F, 3F, 3F is see 0, 0, 1, 1, 1, 1, 1, 1, 0, 0, 1, 1. So by ending this, we clear those orange, dark orange bits that are blitzed from the pixel on the left with the shift of the 4 pixels at one algorithm. So this is a little extra step. It's a slight overhead, but very little overhead, because this is a constant. You can have it on a register, or you can do an end with a constant. It's a very little, because with this great trick we have managed with a reduced gradient from 0 to 63. We have to draw with a max value of 63 on our fire buffer before we blur, and that's what I do. We have, but with this one we do 4 pixels at one, very, very, very fast. And of course we have offsetted this. This should be here normally, and the other one should be here, to be mathematically correct with the original algorithm. But and I don't know if it would be completely correct, because there might be some overlap of the. Oh, maybe it will be. But because it's a demo and it works, and we wanted to avoid offsets that are read in a misaligned gap, this also works. And finally, if we were to do a vertical blur only, so if we only had that, and this would be a shift 1, okay, divide by 2 and not by 4, this would work even much better. I have done this too in some effects. It's great. The horizontal is a bit tricky. And if we did that, this wouldn't be a 63, this would be 127. So and this would change. So you would have a greater gradient if you want, of course. If you want to have a greater gradient, so it depends. So if we were to add way more pixels around, you would have to rearrange things. But anyway, I think I have to stop here, and I guess that's it for this tutorial. See you next time. And I'm sorry that it took larger to explain. It's very hard to explain that stuff. So bye.